Okay, so part three will be visualizing linear algebra concepts like dot product, like plus, minus, like norm, and all these things will be visualizing using NumPy, okay, and Matplotlib. So first of all, let's create two vectors. But before that, let's first create a kind of a coordinate system, so like a canvas. So let's clear our figure, and let's have axes dot set aspect um, equal. Now axes, let's do it within, let's say 10, 10, negative 10, 10. So that shows, okay, so it's actually here. I just moved it from my other screen. Okay, that's our canvas for now. Let's zoom it a little bit. Okay, very good. And let's show the grid. But right now this grid is based on this major text about 2.5 interval. If we want to have slightly different text, we can say mp dot arrange 10, 10, 1. Now you can see that x text becomes interval of 1, and you can do the same thing for y. Okay, got it. On this canvas, here 0, 0 is the origin. Now let's plot some, vectors. Let's say A is a vector, p.array, array 4, 2. Okay, that's a vector. How do you draw it? How do you draw it? Well, you can draw it that way. You can draw it in different ways. You can say plot from 0, 0 to A. So basically like 0, A, 0, and 0, A1. Do it that way. So that shows the line segment. But what if we want to have a little bit better, like a little bit arrow at the end, and a slightly easier way to draw this vector? We can still do that. Let's first try to erase it before we do anything else. Say white. Okay, it's gone. Again, you can see this trace, but really it's gone. Now let's introduce a function called quiver, which is like 0, 0, A0, A1. So from 0, 0 to A0, A1. If you just do it that way, it's drawing a very, very small arrow. It's really not the same scale that we wanted. So the real thing is a little bit complicated. I wrote down in my notebook that is quiver like this. So it got some other parameters, or if you please. So quiver 0, 0, A0, A1. Angles equals XY, scales, you don't need to worry about that. This is just verbatim. Scales 1, and color is cyan. Okay, that is drawn here, but because of the white stuff that we colored here, it's not showing up very nicely. So let's clear everything up and clear figure, then axes, and this. Okay, and axes. Sorry, I should have done this here. So net 10, 10. That's the canvas range, and x ticks p dot arrange. And let's just do this first. Let's see how about if I just say, oh, what if I just say x ticks 1? Does that work? That doesn't work for sure. You have to do np.arrange if 10, 10, 1. Now you do the same thing for y, and okay. Now you grid. You turn on grid. Okay, great. That's our canvas. Now let's do the quiver. Okay. Let's use blue color for the first vector. That's our A vector. Now let's look at our B vector. Our B vector is np.array 1, 3. Where should it go? It should go here. 1, 3, right? It should go here. Okay. Indeed, it should go here. B vector. Let's use red color. This is our B vector. Now, from now on, in order to do it more easily, let's try to write a function ourselves, like draw arrow or just def arrow, point A, point P, from point P to point Q. So we'll call quiver, and let's say P0, Q0, sorry, P0, P1, or you can even do it this way. I believe you can do it from XY to X1, Y1, something like that. So you just say XY to X1, Y1, 1, and whatever color, and color is color. Okay, so if we define this function and then just arrow, let's say from 0, 0 to -2, 2. We forgot one more thing. That is the color of that. Well, what if we just change it to add a default color? By default, the color is blue. Okay. Now here. Okay, -2, 2, right? Okay. And what about +2, -5? Okay. And these are Python tuples, by the way. You should also test it with NumPy tuples. So let's do a kind of mixed way. NumPy arrays. Okay, so 1, -1, for example. Oh, that works. Yeah, as we expected. Okay, so let's erase all these guys. So this, let's just focus on what we need to focus. Let's just erase that. Right, it's gone with a trace. Let's erase this one as well. This is just a funny way of doing erase. And let's erase the last one. Okay. They're all gone. This is A, this is B. Now let's do the vector addition. So what is A plus B? Well, that's element-wise addition, so it will give us 5, 5. But how do you demonstrate it geometrically? Well, geometrically, the addition, the sum of two vectors, is computed using a parallelogram, right? It's kind of a triangle principle, but it's a parallelogram. So like what you learn in high school physics, right? So you have a parallelogram where the four sides are A's and B's. So basically you move this B vector here from the end of A vector and then connecting from the origin to the end of the new B vector, and that's the A plus B vector. Okay, so here if we want to draw an arrow from 0, 0 to sorry, from A, at the end of A, that is this position, and we draw another B on top of that. So this arrow A, B with another red. Okay, let's see how it goes. Oh, it is actually as we expected. So this quiver is not using absolute coordinates. It's like from xy to x plus x1, y plus y1. Okay, so otherwise we won't get this, right? Otherwise we'll get this, right? So yeah, so this is what we have, arrow or vector. We'd better call it vector instead of arrow. So from xy, draw a vector of x1, y1, something like that. Okay, now we can say arrow 0, 0, and a plus b, and let's use cyan. Yeah, so that demonstrates the parallelogram principle. A vector plus b vector, you get a plus b vector, right? So that's what you learn in high school physics. Now, what about minus? What about a minus b? What is a minus b? Well, a minus b, technically speaking, is from b pointing to a, from the end of b pointing to the end of a. So that's the a minus b. So what is a minus b, by the way? A minus b is 3, negative 1. So basically 3, negative 1 should be this direction. Yeah, it's indeed this direction, right? So let's demonstrate that geometrically. From the end of b, you do to the a, and that you use another color. Let's get another color. What color do you want? Green. Okay, good. Oh, yeah, let's do the parallelogram. No, that's not what we wanted. What we wanted, this direction, right? So yeah, so instead of B, so if you say BA, that's from the end of B, draw another A. That's this one, right? So what we wanted is from the end of B, draw an A minus B vector with our favorite color. What color? Our favorite color. What else can we use? Black. Maybe black. Okay. That is A minus B vector, right? And you can, for comparison, you can draw from the origin the A minus B vector using same black. Yeah, so they are parallel to each other, right? So this vector and this vector are the same. Okay, good. So this we demonstrated vector and vector addition and subtraction. Now let's demonstrate dot product, which is the central concept. Very, very, the most important concept, the only thing that is mattering a lot in a machine learning, that's the dot product. That's the single most thing, that is single most important concept at all, okay? Now, before we do dot product, let's review the norm, the L2 norm, or the length of the vector. So you use np dot linear algebra dot norm, okay? So the length of A, or L2 norm of A, is 4.47, okay? So that means this length of the blue one is 4.47. And what about the B vector? It's 3.16, slightly longer than 3 because this is y-axis is already 3.16. Okay, so now let's do the dot product. So as we said, dot product can be interpreted in 2 different ways: geometric way and an algebraic way. Algebraically, so if you just say A times B, that's element-wise product. That's not very different from dot product. Dot product returns a scalar value or single float value. So A times B returns a vector of the same dimension by doing element-wise product. A dot B returns a dot product, which is a single number. Okay, 10. Why is 10? Because A is 4, 2, B is 1, 3, so 4 times 1 plus 2 times 3, yeah, that is 10. Okay. Now, the geometric meaning of dot product is A dot product B is basically the MP, the norm of, let's define norm by the way. So let's just say norm is lambda x MP dot linear algebra dot norm x. So this is a kind of shorthand or inline notation for defining a function. So instead of saying define norm x and return MP dot linear algebra dot norm x, I just use lambda x, okay, which is kind of a nameless function, okay. So you get used to that. Okay, now I just say norm of A. Okay, norm of A is 4.7. Alternatively, you can also say from MP dot linear algebra import norm. Okay, either way, right? Now, where are we? Okay, now if we say A dot product B should have been norm of A times norm of B times cosine theta, right? Cosine theta. So that's the geometric. That's the relationship between geometric and that's the geometric interpretation of dot product, right? So we can see from this equation that cosine theta, that is the angle between A and B, cosine theta, this is theta, should be the dot product divided by norm A and norm B. Okay, so let's try that. So this of course is just the equation, and let's move this around. So let's move this around. Something like that. So this thing is cosine theta. So this is cosine theta. Yeah. So 0.7 is cosine theta. And you can basically recover the theta by doing arc cosine. So if you want to say, okay, cosine theta, and theta is arc cosine. By the way, normally you would need, import math, arc cosine, but now we are under NumPy framework, NumPy environment, so you just say arc cosine, because you had the PyLab before. Arc cosine, this whole thing here. Okay. Okay, now what's your theta? It's 0.78. What is this 0.78? If you, this is in a pi notation, right? So if you kind of convert it back to the degree notation, so divided by pi, mp dot pi, I think that's the mp dot pi times 180 degrees, it got 45 degrees. Really? Is it coincidence that the angle between A and B are exactly 45 degrees, which is half of the rectangular 90 degrees? Is it really? Yeah, it does look like it's 45 degrees, right? So, and we can further verify that, right? So really, it's 45 degrees, okay? And you can verify the angle between this b vector and this a minus b vector to be 90 degrees, and their dot product should be exactly 0. So let's try that. So if b dot product a minus b, okay, so that one should be 0, okay, because these two are exactly perpendicular to each other. Yeah, so indeed this is 45, this is another 45. You can actually see it very easily. So this b vector is 1, 3, right? X-axis 1, y value 3. This a minus b is 3, 1, so they have to be perpendicular to each other, right? Now the last thing we want to talk about is the projection idea, or concept of projecting one vector onto the other. Okay, so this is deeply connected to dot product, right? So how do you compute the projection of b vector onto a vector? By the way, the projection of b vector onto a vector should be of this length here, right? So if you kind of add a kind of a line that is perpendicular to a vector, that would end here, right? So this vector is the projection of b vector onto a vector, and how do you compute that? Well, we use dot product. Okay, so So basically the idea is to say, well, dot product is basically a vector, a norm times b norm times cosine theta, and this projection is basically b times cosine theta, right? So by the way, so this is basically cosine theta. Let's do this again. Cosine theta. Right, cosine theta is 0.707. Now, the length of b norm times cosine theta is exactly the length of the projection. So 2.223. So that's the length of the projection. And to draw that length, to draw that projection, we just need to do it proportionally onto the a vector. So basically say a vector times this new length that you want it to be. And so you can divide the norm of a first times the new length that you want it to be. Okay. What is that? That's exactly 2, 1. 2, 1. Okay. So let's call that a c vector. And that is the projection of b onto a. And we can arrow it. C vector using a new color called, well, orange. Does it have orange? Yes, orange. Okay, so this orange is the projection of b onto a. And to compute that, it's also very easy. It's basically a divided by norm of a. What is a divided by norm of a? A divided by norm of a is the unit vector in that direction. Okay, so that's how you convert a normal vector to a unit vector times the wanted length, the targeted length that we want it to be, which is computed by norm of b times cosine theta. What is norm of b times cosine theta? Well, it's exactly norm of b times a dot b, the dot product, divided by norm of a times norm of b. So the norm of b actually cancels out. So really, you can compute it by saying, so if we do a little bit of math, so c is a times norm of a. So I'll write it here, but it's not in a non-pi notation. It's in a kind of a mathematical notation. Okay, so this is unit vector of a, right? Now times the dot product is a dot product b divided by norm of a. Okay, so in other words, you have a divided by a square times the dot product. Okay, and let's translate that. So this is our, we can just recover this, divided by norm of a. Okay, which is a divided by a norm square times a dot b. And let's say this is our comment. And let's try this. C, let's use a D. It's a times a dot b. I don't need this. Divided by norm of a to the power 2. What is d vector? D vector is exactly the same as c vector. Right. Well, so what is c vector? C vector is here, but d equals c. That's quite different from d. So yeah, so this is slightly this element-wise comparison. But why it's returning false instead of true because there are kind of floating point issues. So don't worry about that. Now, if we just want to plot d, plot arrow 0, 0, d using a color of magenta. Yeah, so it's exactly the same. D is the same as C. Okay, so this equation here or here is exactly the equation that you use to understand Myra. And in exercise 2, you will need to kind of manually derive that equation. It's much simpler than the perceptron convergence proof, believe me, but it just needs your geometric understanding of dot product and the projection idea. Because the projection idea is so central that it's basically the geometric margin. So if A vector, the blue one, is the weight vector, and B vector is the x vector, or the training example, then this distance is the projection of x onto W, which is basically the geometric margin. The dot product itself is the functional margin. The geometric margin is really the Euclidean distance, right, in that direction. So the projection idea is very, very important. Okay, and I hope you have understood this idea of dot product and projection of one vector onto the other. And you have to be able to understand that in order to understand Myra and SVM. Well, Myra is not necessarily that important, but SVM in the coming week is super important. Okay, let's end here for this part.